standalone proof of the Cauchy-Resty theorem, which is fairly simple, and how to calculate residues very easily. And then we're going to go over some examples, simple examples today, okay, of applying Cauchy-Resty theorem to calculate infinite integrals. So what we saw last time is the following. If a function f of z has some singularity within a domain, the expansion that we give is Lorentz series expansion. So f of z say has a pole of order n at z equal to z naught, then the corresponding series that expansion that I can give is the Lorentz series expansion. This is what we did. So I can write f of z as an infinite series where n starts from negative n, because it has negative powers of z minus z naught. So this, whatever is the order it has of the pole, you must have this to infinity. That's the difference, okay? So the Lorentz series, if it is minus infinity to infinity, you got z naught is an essential singularity. Z naught is a pole of order m, so this summation has to start at this point, okay? Because what we know is Lorentz series has, if I wrote it in full, it is negative am. This is what it is, right? I mean, this part is an analytic part. Right. So if a function is pole of order n, so this concise notation really is representing whatever I wrote. Okay? And a minus 1 is the residue of the function, and that's what comes in Cauchy-Resty theorem. And last time we tried to calculate a by expanding and looking at the coefficient, but I'm going to give you a simple way of doing all these things. All right, so this we have done. And since we also did previously, so we have a domain, and the function is not is exploding at z equal to z naught, but everywhere else, let us say it is singular, it's analytic. So what we did was, I had to prove one of that came as a corollary to the Cauchy's theorem, that we call this as C and this small circle is gamma. What we also had said was, in this regime, f of z is analytic because we have excluded the point where it was blowing up with this, by drawing that circle. We said that contour integral of f of z dz on the bigger circle is same as contour integral of f of z dz on the smaller circle of radius. This is what we want to define. Okay, let me just define all these things carefully for you. Let's call this radius as rho of this circle. The radius of this circle is rho, and let's say radius of that circle is r. Okay, rho is a smaller circle. Z is any point on this smaller circle, let us say. Okay. So this is what we said, right? I mean, this can be as small as we want, and that r can be as big as we want. So we want to look at this in the limit rho tending to 0. Rho is the radius of the smaller circle. So this also we had proved previously. Now for f of z, because at z naught, it is blowing up. So the function I can, for that expansion of the function f of z around z naught, I can give a Lorentz expansion, series expansion. So let me substitute for f of z that, what I have written here. Okay. If I did that, I have an, what we're trying to say, can I come up with an expression for continued integral of f of z dz on the bigger circle, right? So f of z dz is in this case nothing but n minus infinity to plus infinity of a sub n z minus z naught of n. Okay, so all I've done is nothing but substitute for f of z from Lorentz series, and I'm calling it as dc at this point. All right. So I'm going to evaluate the value of the integral on that smaller circle. All right. Now, on the smaller circle, if z is the variable on c, what is it, gamma, z minus z naught, you have to learn to run. Because my origin is, this circle is centered on z naught. What is z minus z naught, the complex variable? How do you write it? Rho is the radius of the smaller circle. How do we write it? How do you represent the complex variable? Rho I, yeah. So we can write, right? So I can write this guy I can write it like that. And dz is nothing but rho is constant, it's only the angle which is changing, right? I can always write dz as that. And so this integral is nothing but, again, let me just write down first. They're going from in this anti-clockwise, so 0 to 2 pi. So I can now, the variable I can change z minus z naught is root of n. dz, I'll get 1 from here, root of n plus 1, exponential of I, n plus 1 theta, d theta. I also written, I have I from here, so I have this. Is this clear? Can I erase all these things? All right. Now I'm going to separate here the term n equal to negative 1. Okay. N equal to 1, root of 0 is 1. That is, all I have is this term. And the other term that I have is when n not equal to minus 1, I'm going to plug that in one location. And that is nothing but a sub n, rho n plus 1, 0 to 2 pi of exponential of I, n plus 1, theta, d theta. Right? I is there. What is this integral? Exponential of I, n plus 1 theta, d theta, 0 to 2 pi. What is that? At 0, because cosine, let's say, the integrate 0 and both limits are the same. So this is gone. The only time this integral contributes is when n equals, that's why I separated out. this is what? 2 pi I times a minus 1, which is your residue of the function. Okay, so 2 pi I a minus 1, which is your the coefficient multiplying the term 1 over z minus z naught, which is the residue of the function. So we have proved contour integral of f of z dz, where f of z has singularity in the domain. Okay, right now we consider one singularity, at z equal to z naught, and this is nothing but your Cauchy residue theorem. This is the central theorem of this. Right. Just said it's a function of singularity, Lorentz series expansion. And okay, it has got singularity in this domain at some point z naught. Okay, let me just try to exclude it. So I just draw the small circle and exclude it, right? Then we also know that now that if you exclude it, then the function is analytic in this region, in this angular region and along those contours. So I can also say the value of the integral, contour integral on the bigger circle is same as the smaller circle, and on the smaller circle, we know how to write this f of z function, right? And we're also going to make rho tending to 0 in some sense, right? I mean, so this is going to 0 anyway, all right, because of the explanation and all that. But generally, I can, reduce that radius and see what happens to that integral. Now, if there are more than one singularities, as I said, we have to really the contour integral in a given problem. You may have several such things. So we have to calculate basically wherever it is, we need to exclude all those points. So you have to, depending on what is within your contour C, the big contour C, you have to calculate the residue at all points. So I'm going to write it down. The most general way to write it is f of z dz. Contour integral is nothing but 2 pi I times, I'm going to use this notation just so that you know. Let me just say residues are whatever it is. So R is nothing but a minus 1, okay, residue. So I'm getting away two subscripts, I will just put in this. So you have to calculate residue of f of z at all singularities enclosed within C, within your contour. Okay. And the nature of singularities could be simple pole, pole of order n, whatever. So we need to now know how to. So this looks like a very simple thing, except I need to know how to calculate residues of function. So, if you did not know brute forces looking at Lorentz expansion, try to expand and look at it. And that's too complicated most of the time. So let us now talk about how to calculate the residues in a simple way. Okay? Again, I'm going to prove it starting in Lorentz, but that's the formula you use eventually. Maybe write down the formula and then I'll justify where it is coming from. given by the following formula. N minus 1 of included it with respect to z. Of f of z multiplied by z minus z naught to power n, and you have to calculate all these things in the limit z going to z naught. Okay, so this is that. I should put this small. This is one of the formulas you can use. Of course, you can use Lorentz series itself. So where does this formula come from? Okay, let me just, this is pole of order n, right? Supposing it's a simple pole, what happens to it? What do we mean by simple pole? What happens to this formula for a simple pole? What do we mean by the word simple pole? Function s is of the form 1 over z minus z naught, that's it, right? M is equal to 1. So if m equal to 1, this is 0 factorial is 1, this is 0. So for simple pole, the formula is very simple. Residue is nothing but calculate this quantity in the limit z going to z naught. Everything has to be evaluated in that limit, right? Because this is, you don't have to take the derivative if m equal to 1, right? So f of z times z minus z naught of m, and what do we, and then calculate it, okay? So that's the formula. But let's try to understand, let me write down that here and then try to see where this comes from. For simple pole, residue is given as f of z, z minus z naught of m, limit z tending to z naught. All right. Let's go back to the function has pole of order n. Okay, so back to, that means f of z is of this form. The Lorentz expansion is of this form. The analytic part is infinity, right? Now, so my goal is to, this is the expression if the function has a pole of order n at z per z naught. My goal is to extract out a minus 1 from this expression. So what we're saying is, let's multiply f of z by z minus z naught of m first, okay? If you did that, what will happen? This has got is a to the power minus n, it's a constant, okay? Here, you may have z minus z naught, okay? But this term, what happens? You will have z times z minus z naught or n minus 1, and others will have, you know, powers of z minus z naught, right? So the first term, I'm just, it's just a minus n plus 1, multiplied with z minus z naught, right? So I will have z minus z naught, so on and so forth, and a minus 1 will have a minus 1, and this is a naught z minus z naught upon m. Others will have higher powers of m in it. Fine. Now, then you say, okay, doesn't help me. If I take m minus 1th derivative of this thing in this quantity, what happens is these terms will start dropping off, right? Because this is a constant, blah, 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 all these things will start dropping off. And then this term will become what? M minus 1, z minus z naught of m minus 2, blah, 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 and then what? So that is a m minus 1 factorial will develop here. A minus 1 will be there. And the rest of them will always have z minus z naught in it, right? So all of this I'm just combining into one term, but you can see it is some factorial of m, and but all of them will have z minus z naught, okay, something. There Bn is really some combination of n factorials. Okay. Now if I put, this still doesn't help, right? Now I have to get rid of that, so the other term, so I have to put limit z going to z naught. Okay, when I do that, these terms, the analytic part of it after you do the m minus 1 derivative, that will drop off. Okay. So that's why you have a minus 1, which is the residual function, which is the same as a minus 1, is nothing but 1 over m minus 1 factorial of this whole thing. Okay. M minus 1 derivative of the original function multiplied by z minus z naught, where the singularity is 2 power of m. All this you have to evaluate. Limit z going to z naught gives you a minus 1. So that's the origin of this expression, where it comes from. Again, it's coming from Lorentz expansion. Okay, so we know that's how it should be, the behavioral function, and I have to somehow get that extracted term, and that's how that formula was proposed. Is this clear? I'll be on the formula, but let me just maybe show the how to use it. We had what was it we were doing last time? Z minus something.
Plus 1 is equals to.
No, that was on the, or maybe I didn't give you that. Okay, I was going to give you that was a Taylor's expansion, was a bit complicated. Okay, so let's say this is the function. What are the poles and singularities of this function?
Follows 3.
No, but where is it lying? And order of the pole. You got 2 poles. Z equal to 0 is a simple pole, right? Z equal to 2 is what? Pole of order 3. We have two of them, right? The function will blow off and z equal to 2 and also z equal to 0, right? So both of them are singularities of this function. but one of them is a simple pole, the other one is pole of order 3. Okay. So the residue, if both of them are enclosed in your whatever contour you are doing, then you have to calculate residue of the function of f of z at z equal to 0, as well as residue of f of z at z equal to 2. Both have to be calculated. Now, what is the residue of z, f of z at z equal to 0? How do you calculate that? It's a simple pole, right? It's not repeating, right? And
We're just gonna get left with f of z, z minus z naught to the m.
right, m is 1, that's what you have to do. For simple
yeah.
pole, m equal to 1, that's what I, so all I have to do is, yeah, sorry, m is equal to 1, so I have to put m equal to 1, sorry, I should have removed it, m is equal to 1, so that's all it is for the simple pole, okay. So residue is simply, residue at z equal to 0 is simply equal to limit z going to 0, I have to multiply by z minus, z naught is 0, right? So z times z minus 2 whole cubed, that's what it is, and z can be cancelled. So it is nothing but negative 1 over 8. Okay? Z naught is basically 0, right? Now, okay, z minus 0, z naught for the first problem. Z naught is 0. So I'm writing z. That's why I wrote it like that. Okay, so negative 8. Now what about the second case? This is pole of order 3. Right? Z equal to 2 is a pole of order 3. It's not a simple pole. So what is the formula for calculating the residue? Can we write that? Limit z going to 2 of n minus 1 factor is there, don't miss that, okay. 3 minus 1 is 2 factorial. I have to take the second derivative in this case of f of z is a kind of thing. So I have z minus 2 whole cubed 1 over z minus 2 whole cubed, they have to do, and this sort of eliminates the singularity kind of a thing. So second derivative of 1 over z, you calculate and then you take the limit. You do all these things and take the limit. So what is that? First time you need to take the derivative is minus 1 over z squared, right? So this is nothing but 1 over 2 factorial of d over dz of 1 over z, limit z going to 2. So that is negative 1 over z squared, and then you have to differentiate one more time. So that is nothing but and then I have to still, don't forget the limit that you have to take. So that is what? Equal plus z cube? Yeah, and the 2 will cancel, right? I have 1 over 2 factorial 2 over z cubed, limit z tending to 2. So this 2 and 2 I can cancel. So it's nothing but 1 over 8 plus 1 over 8. so in this case, the residue is 1 over 8. So important thing is, if it's second order pole, still m minus 1 will be, don't forget the factorial, okay? That's an important thing, you get an answer. So it's 1 minus m minus 1 factorial. The reason why it comes, that's why I go back to the definition, we have to differentiate m minus 1 times, then, the coefficient develops into factorial. Yeah.
And like that's the a minus 1 in the Lorentz series, right?
Yeah, this is exactly. When I say residue, it's always the term a minus 1, okay? So if you don't remember any of these formula, what do you have to do? You just have to make z minus 2 equal to u or something like that, make the transformation and make sure, then this will become something like, 2 plus u or whatever it is, and you need to expand that in terms of geometric series or binomial series, and then look for the coefficient, which is coefficient of 1 over u, which is same as coefficient of 1 over z minus 2 or something. So it can become quite messy,
Okay.
but for z equal to 0 may be simpler, but I'm just saying, if you don't remember anything, go back to the basic principle from where the residue was defined, okay? That's always the easiest. That at least you know where it is coming from, because this formula you may forget, okay? Whereas that is easy to remember, it is a Taylor series kind of a thing, except it starts from wherever the pole is, or to the pole at infinity, and you have to look for, you have to expand the function into series. Basically a function into series if you know how to expand it, you have to identify the coefficient of 1 over z minus 2 in one case, in the other case coefficient of 1 over z, because we have to do Lorentz expansion around z equal to 0 as well as z equal to 2. So there will be two different Lorentz expansion, and you have to identify. So if you forget, that's where you have to go. Go back to the brute force method. Like if you don't know how to differentiate, you go back to the original definition. Keep on doing that, right? Something like that.
So we have more. So like you said, we'll have two series for the function if we expand it out.
What did you say?
We'll have two Lorentz series.
Yes, one corresponding to z equal to 0, one corresponding to z equal to 2. Yeah, it will be two different, because that Lorentz series is expansion around z equal to z naught. We have z equal to 2, z naught equal to 2, z naught equal to 0. There are two singularities in this problem. That's why I gave that. So in a given problem, you may have several singularities. A function may be blowing up at z equal to 0, whatever, z equal to 2, whatever it is. It can blow up at many locations, right? And if all of them are included, then I have to, supposing both are included, I have to calculate 2 pi I times residue of the function at z equal to 0 plus 2 pi I residue of the function at z equal to 2. Okay, so I cannot just stop there, because they are both included inside your contour. Okay, so that's the most general formula. But that's why you have to draw the contour cleverly, so that only one is included or something, you can eliminate or something. Then that makes your job easier, right? You don't have to calculate residues at two locations. All right? All right. Now, I'll give you one more formula before I do a problem, applying it, right? That's the most important.
What if we
thing.
have multiple orders for the same z?
Yeah, for the same function on f of z.
Yeah.
Yeah, it can be any function. Yeah, you
We
can
just
have-
add them together, we just add them with the summation?
Yeah, you can have. I could create a function like this, right? Whatever it is, then pole of order z equal to 1 is order 2, z equal to 2 is order 3, this is order 4, right?
Okay.
It is up to us. It depends on the function you are trying to integrate, right? It is the integrand of your problem.
So we would do multiple Lorentz expansions for
Each one, yeah.
Wow.
That's why we need this formula. You understand?
Yeah, okay. And then we would just add them up, like.
Yeah. That's why going back Lorentz expand all the time for multiple singularities is a pain in the neck. Even one is a pain in the neck. But multiple, this one is easier. You just have to, differentiate or not even differentiate with a simple pole or something, right? You can do this more easily. So I'll give you one more formula, which is also useful. Okay, I mean, this is useful when you have rational expressions in the denominator, okay, or trigonometric function, sine z, cosine z, and stuff like that. Supposing I have function of this form, okay, something in the numerator, something in the denominator, okay, like z over z squared plus 1, okay, I mean something of that nature. And g of z is analytic in the domain, and h of z for z equal to z naught becomes 0. It's analytic in the domain, but it has a value. It's a rational function. It can become 0. So if you have such a function, then what we know is, given you have expression like that, I mean h at z equal to z naught is 0. And this is defined in some domain. I mean, it's a big domain, but h of z is 0 at some point. The residue of the function in this case is given as the numerator is evaluated, which is analytic, you evaluate z equal to z naught, where this has a 0. So this is 0 of the function. Okay, z naught is this h at 0 is 0. So whatever it is 0 of the function. Okay. So this is nothing but so you evaluate the numerator at z equal to z naught, where this function, let us say it is x squared plus 1, okay? This is going to be 0 at x equal to plus or minus I. So you have to calculate both of them, of course, both locations. And so it may be useful in certain cases. It's even easier than differentiating, because you just have to look at the denominator, just take the derivative of the denominator at the place where where the root of the function is, and evaluate it, right? So I don't have to look. It's a much simpler expression. Where does that come from? This is otherwise analytic in the domain, right? I mean, h of z by itself. F of z may not be blowing up at z equal to z naught, but h of z by itself is analytic in the domain. Okay, so I can always, if it's analytic, I can always write what? A Taylor's expansion. Right? With the denominator, again, like this. And if you want to calculate the real function at z equal to times, it's like this, that one, right? Z minus z naught times f of z, limit z going to z naught. Okay. So if I know f of z is that, okay. So the residue of the function in this case is nothing but z minus z naught g of z, and this is 0 because by definition it has a root. Okay, that's what I'm saying, the function has a root at some point. That means this is 0. Okay, that's given. H of z naught is 0 at that location. So I can factorize z minus z naught out. The first term in the denominator is h prime z naught. Then have other terms, h to the 1, z naught over 2 factorial, z minus z naught, and high powers of z minus z naught is there. So this and this can cancel. So in the limit z tending to z naught, what happens is then these terms become 0, right? The only thing which remains is that. So this is why you have the formula is simply the value of the function and the numerator at z equals z naught divided by the denominator, the first derivative of the rational expression, something you have, you take the first derivative of that at z equal to z naught. Okay, h prime is the first derivative of the function, the denominator. At z equals z naught, and for which h at z equals z naught is z. That's the root of the function. Whatever is you have the origin function. If it becomes 0, z naught is the root of the function h of z in the denominator. Okay. Let's do an example so we can understand.
So the top equation on the denominator, that's just Taylor expansion, right?
Yeah, this one, right? Yeah.
Okay.
This one, h of z is analytic in the domain as such, okay? All it becomes 0. It's not blowing up at h equals 0 is 0. F of z is blowing up at z equals z naught, but not that, right? So I can make Taylor's expansion of h of z, which is function at z equal to z naught, first derivative z minus z naught, blah, blah, blah. And we are also given that this function, because that is the root, z equal to z naught, root of that term is 0. And the higher order term will become 0 because, because we are letting z equal to z naught. When you do that, higher order terms will become 0 because this is the only term which is going to survive when we take the residue of the function, because you have, it's like a simple pole, so you have to multiply by z minus z naught, so that cancels out. So only term which survives is the first derivative of the denominator at z equal to z naught. That's all I got. So it's a fairly simple one. In many cases, it may be even easier. Okay. I mean, even the same example we could take. What was that we just did? Yeah. But normally I try to use it for trigonometric functions or something, but or algebraic expression was there. Let's just keep one function at this point. Okay, z, let's forget about z. Okay. For me, f of, the numerator is 1, g of z is really 1, okay? Even if you had, doesn't matter, let us, I want to calculate residue of f of z based on this at z equal to 2. Let's see what happens. G of z is 1. Okay, nothing I have to do. And then I have to take. Let's do this for, because I think that because it becomes easier. Okay. It's 3. What happens? The formula was is g at z naught divided by h prime at z naught. Okay.
So the denominator has to go to 0.
It's equal to a root of the function. Okay, no, that's the root of the function. So that's a good. Okay, what I should have is something like, let us say I have a, yeah, let's have a function like this. Okay, I mean z squared plus 1. Okay, then the root of the function in this case is z squared equal to minus 1 or z equal to plus or minus I. Let's say. Okay. So we do have a root of the function. Let us see for that case, what happens is g, or we can even do it from the other method, just so I want to check how the method works there. So the numerator is what? It's 1, right? I mean, that is not something I can do anything about. It's a constant. The denominator is 1 over 2z, right? And this has to be evaluated, let's say, equal to z equal to plus I. So this is 1 over 2I based on this formula. Okay, if I did it the other way around, this is simple code, right? Because it's not z squared plus 1 whole squared. So z equal to plus I is a simple code. Right? So the residue of f of z at z equal to plus I is nothing but, using that formula, is z minus I, z plus I, z minus I. You have to calculate in the limit z equal to I. Right? So I can cancel that, and it is 1 over 1. So what you want is a rational expression, and you want to calculate the root of that function. When that term becomes 0, I mean, in this case, something there. But most of the time, is useful for something like this. Supposing I have a function f of z, and I want to calculate at z equal to 0. In this case, it's not easy for me to know how to do it. So then I can use this formula very easily, because z equal to 0, we know it is becoming 0. So the residue is simply of the function is exponential of 0 over cosine of z at z equal to 0. So it is simply 1. Okay, so whenever you have trigonometric function, definitely use this method. Okay, it's easier, and you have some algebraic, an expression like ax squared plus bx plus c kind of a thing. You know how to calculate the root of that function, right? And of course, both, I just calculate z equal to plus I. If you inside the contour, you have to calculate for that also. But that's a general method, These are the two methods which are most handy for easy for you to calculate the residue of the function. Okay. Basically, you have to find the root of the denominator, not of the entire expression, because you may have numerator some comes from 0 also. Only the denominator we're looking at in this case. All right, let's do some examples, simple examples, so that you understand how we are going to apply this. Okay, maybe this is a serious example that I can illustrate with. You're asked to calculate an infinite real integer. Okay, so x is real. Right? So our Cauchy residue theorem is applicable for a closed contour, right? So instead of this, I'm going to consider a closed contour. I mean, you just write a complex analog of the integrand. Okay, first step. if I wrote it that way, then I know what that integral should be, right? My integrand is 1 over 1 plus z squared, and I need to know the residue of that function. So this is nothing but 2 pi I. From here, whatever you calculate, I have to then go back and extract whatever I want, residue of f of z is the integrand here, okay? Whatever the poles are, I leave it to z equal to, we got two of them, we need to check, okay? I mean, z1, z2, whatever it is, on the, we have to calculate that. If there are several of them, I need to calculate that. Now, so first then, the integrand you have to analyze. The integrand is f of z, so the pole 1 over 1 plus z squared. So it goes at what? Z equal to plus or minus I. Right? And I need to get that, okay? So I can think of a contour like this, right, for this problem. So that is my real, imaginary z, and this is real z. And z equal to plus or minus I. Right? If I chose a contour like this, although I got two poles, the integrand has got two poles, z equal to plus I is here, z equal to minus I is here, right? Why did I choose a semicircle rather than a closed contour? Because I want to calculate that kind of integral, minus infinity to plus infinity, right? So you just choose a semicircle like this, and choose a semicircle of radius r, and we'll calculate the integral. Look at this integral then, r tending to infinity. So we just keep on enlarging this and look, see what happens to the contour integral when r becomes infinity. Okay. So what is the residue of the function? If I chose that contour, so this says calculate all the residues within the contour. Okay. So although it has got two poles, I have to calculate the residue only at z equal to plus I, because that's the only one which is in the upper half plane, right, in the circle that we're enclosing. And that's what we had calculated a little bit earlier, so it's a simple pole, so let's just limit z point I. Okay, so this is here, not there. So this is nothing but 1 over 2i. So we know I'm not going to calculate all of them, only z equal to plus I. Okay, that's the only one I'm going to calculate. So my right hand side is nothing but 2 pi I. Residue of the function is 1 over 2i. So my right hand side is nothing but pi. The right hand side of your Cauchy residue theorem is just pi. Because this is, residue is calculated using that formula, right? Which is 1 over 2i. And the Cauchy residue theorem says closed contour of f of z dz is 2 pi I times residue. So you have to calculate that. Now this part, we need to break into different parts, closed contour. And what is that? If this you understood, I'm going to write my right hand side as pi. This is, I'm going from minus r to plus r. Okay. I'm traversing on the real axis, so I can write it as 1 plus x squared. And then when I'm on the upper half plane, its complex variable is r. Z is nothing but r exponential I theta on everywhere here, right? So that is nothing but dz, if z is r exponential I theta, dz is r exponential I theta, I d theta, right? So I can write r exponential I theta, I d theta for the numerator, and the denominator is 1 plus r squared exponential of 2I theta. And I'm going from 0 to pi, right? Now theta, r is constant, so if the variable is theta, theta is 0 to pi. Now we're going to examine this integrand in the limit r tending to infinity. What happens to this? Because I also have to get back infinity, because that's what I'm interested in. So what is happening to the integrand for r tending to infinity? R is very large, so I can write the denominator as r squared exponential of 2I theta, right? So this integrand, in this case, is becoming the denominator is approximately equal to 1 over r squared exponential of 2I theta, right? I can write it like that. So it is 1 over r times all those things. So I can approximate this integral as follows. This is minus infinity to plus infinity. Let me write r in the infinity. Minus r plus r dx 1 plus x squared plus I. This is becoming 0 to pi of r exponential of I theta. I can approximate this is r squared exponential of 2I theta d theta, right? So it's nothing but plus I over r exponential negative I theta d theta 0 to pi. So that's the left hand side. This is equal to pi. That's coming from the residue calculation. So for r tending to infinity, this will become 0, right? So what we have is minus infinity to plus infinity dx 1 plus x squared. There is nothing but pi. Is this clear, method? So, so first you look at the integrand, examine the first where the singularities are, how many singularities are there, nature of the singularity, simple pole or multiple pole. If it's simple pole, use the simple formula. If it's a pole of second order or higher order, use the other formula to calculate the residue. And choose a contour. The contour will be decided by the limits of the problem. What I have to calculate. Is it a circle or full circle, semicircle, everything will depend on the integration that we want to perform. Okay? And in this case, it's easy to the complex analog of the real infinite integral I want to calculate is very simple. In some cases, it may be some weird thing. It may not be, sometimes it's sort of not totally related to the function also, but yet you can get. I mean, most of the time it's not like when it is sine, let us say, is there. Something sine, you always use exponential I zeta. Let's say sine of x dx, something like that. You always use exponential I z, and then get the imaginary part of whatever integral you have calculated. That is easy. But that with the natural log and all, sometimes it is something weird actually. It may not even be, but you can get because you can make some of them go to 0 or something. So there are some tricks to guess the integrand to get whatever you want. So, so the choice of the contour is important. How to calculate the residue is important. For the rest is actually very simple. So the method, if you know the Cauchy residue theorem, it is very simple. Okay, to calculate certain integrals. What's the time? Maybe I can do one more problem to illustrate. Let us see. Maybe continuing on the same theme a little bit easier. We'll do some more difficult problems later on.
In what cases will we have a negative I portion?
What did you say?
In what cases will we have a negative I portion?
Which negative evolution?
Well, we just have the, I,
And then
Yeah, but this is what I'm going to say. You can take this problem and try to do, I should get the same result if I close the contour. The Cauchy theorem does not tell you, it just says closed contour, okay? It's the same integrand, but now you're going from pi to 0, you know, so you may have to do something and the direction of the contour is changing, maybe the sign becomes whatever it is. So, so we have eliminated that, but the same problem, the same integrand, you should be able to get the same result. If I went from minus r to r and I closed it this way, okay, and I'm including the other one, you should get the same result. It should not depend, because the Cauchy theorem says only closed contour.
okay.
So
but
there may
what
be
part
cases, yeah.
What part of the problem, made you decide to use that contour?
What do you say?
Just the half shell?
Yeah,
What part of the problem made you decide to use the half shell instead of a full shell?
because then I have to, if I do the full thing, first of all, it's 0 to 2 pi. That's not my, the limits of the integral that I'm interested in calculating is dictating that. Okay, if I did this, it's 0 to 2, we'll do a problem, okay? If I have a problem, the limits of the integral is 0 to 2 pi, okay? The limits tells me what type, also tells me what type of contour I have to do. In that case, I'll do a circle, okay?
Okay.
Because whereas here I wanted minus infinity to plus infinity, so I have to go on real axis, you understand? That's the reason I did that. And there may be problem is asking you to calculate 0 to infinity, okay? And if the function is even, then I look at the example, because again I would like to see, can I do like this, semicircle, right? If the function is even, I'll try to make, half of minus infinity to plus infinity. So I will try to evaluate this integral if the function is even function, right? And I know how to calculate, I know how to draw the contour for such a thing. And then I'll half that, what I calculate this, and I'll half that integral to get the actual integral I'm supposed to evaluate. So some of these tricks we have to learn, depending on what the limits of the integration that you're trying to that you're asked to calculate. Okay, minus infinity, 0 to 2 pi, or 0 to 1, some of these things. So it's a limit which is sort of a little bit telling you what type of contour to choose. Okay. All right, let's see. Okay, I think we got such a problem. What I was trying to say. This thing over here. All right. So this is an even function in x, right? Numerator, denominator. So instead of this, I will try to calculate this integral, which is half. This integral exactly that. Sorry, is 0 to half of minus infinity to plus infinity, cosine of x 1 plus x squared dx. Right. Now, with the Cauchy-Residual theorem, I'm going to apply it to this integral. Okay. So I will calculate an integral I prime, which is this. I'll try to get this calculated, and then I'll calculate that back. Now, so that's a real integral, right? I need to get a complex analog of this. Don't write just cosine z1 plus z squared, okay? That's not good, okay? So I need to, because that's a typical mistake people make. So the complex analog of this integrand, I can try. Although this is on the real axis, I'll try. I need to calculate to apply Cauchy-Residual theorem some closed contour. I have to calculate this integrand. This is what I will try to calculate. From there, I'll extract that. From here, I'll extract that. Okay, so that's a process. I will try to, this I know how to calculate through the Cauchy residue theorem.
Do we still have a 1/2 on that I prime?
I will come back to that, right? I mean, this is the I,
Okay,
that's why I call it I prime. I prime is just this one.
okay.
Yeah, and so that you, I remember to put half factor towards that. Okay, so I'm not calculating the original integral I had to calculate, but I want to calculate this integral. But this integral I'm going to, instead of this real integral, this is what I'm going to calculate. And from there, I'll try to extract this. Okay, the real part of that will eventually give me that. So this is similar to what we had, z equal to z square plus 1 equal to 0. So z is plus or minus I. Those are the poles. And the pole is simple. And if I used a semicircle in the upper half plane, only z equal to plus I will be calculated. So what's the, I'm going to use that. Okay, I don't need that. Get a simple pole, I can erase this. Alright. So what's the residue of this function? If this is my integrand, what is the residue of my function at z equal to plus I? I'm also going to choose a semicircle in the upper half plane because I need to go from minus infinity to plus infinity, right? So I will traverse similar to that what we had. Okay. This I'm going to ignore, the other one, because it will not appear in the Cauchy residue theorem. It's there for the integrand, but it's not there. Okay, so simply the same thing, right? So my integrand here is exponential of I z, z plus I, z minus I. Since I'm trying z minus z naught, I have to multiply by that. My pole is imaginary I, and then calculate what limit z going to I. Okay, so I can first, this is within it, sorry. Cancel that. So I have exponent z I squared is minus 1, right? Divided by I. So that is my residue. Z equal to I is I squared is minus 1, right? And then, so it's 1 over 2I e. Z equal to plus I, that's there, right? So I have something of this nature. 1 over 2I, I was taking this the value is 2.7 something, right? Now that is residue. But the theorem says this is equal to what? Don't forget the what I want to calculate is. Okay, so this is equal to what? According to Cauchy's residue theorem, this is equal to what? 2 pi I times the residue of the function, which is 1 over 2I times E. So I can cancel, it's nothing but pi over E. Okay? So it's not enough to calculate residue, it's 2 pi I times the residue of the function is what is on the Cauchy residue theorem. Okay, so that's why this 2 pi I comes. Then I split this integral in two different parts. Okay. Break that into minus R to plus R of along the x-axis exponential ix 1 plus x squared dx plus the upper half plane. This gamma is only the upper half plane, okay? Exponential iz over 1 plus z squared dz equal to pi over e. The same argument, whenever you're, this is what, we cannot apply blindly the Cauchy's residue theorem to any integrand. If f of z has this property that z times f of z, any function which is z times f of z, as z tends to infinity goes to 0, for such function the integration in the upper half plane over the semicircular arc will go to 0. Okay, so that is an important thing.
Can you explain that first term
Yeah. Yeah. I'm
for the
gonna-
integrand going from negative R to R?
Okay, so I have to calculate this integral, right? I mean, this is my goal. I have to calculate minus infinity to plus infinity. So I'm just choosing a closed semicircular arc. I'll make R go to infinity, I'll get minus infinity to plus infinity. And I'm going on the real axis, so Z became X.
Okay.
But here, we are on the upper half plane, so it's a complex variable. The variable there is Z is R to the power exponential I theta. Any point here, the variable is R exponential I theta. Along this, it is purely real. Okay,
Okay.
so that's why so we are trying to eventually calculate real integral through the complex integral methods. That's what we are trying to do. Okay, so R tending to infinity, this guy is 0 for the same reason, okay, because this is going as 1, if it had been 1 over plus Z, that's what I'm going to next time talk about. Supposing you may have a function which is 1 plus Z. I'm in trouble, I just, can it become 0, There's another theorem called Jordan's lemma, which we'll use. Because it's a Fourier integral, I can show it can become 0, but it's not automatic, you have to think about it. But if I didn't have that and had only 1 over 1 plus Z, no, I'm in trouble, I just cannot make that 0 because R to I theta, they will cancel. There's no way I can make that integrand go to 0. I may have to evaluate that integral on the upper half plane, on the semicircular arc. So this is why this theorem is very important. Let me just finish this and tell you about. So the nature of the integrand that you are trying should be such that f of z times z goes to 0 as z tends to infinity. It's the same as r times whatever the radius of maximum value of the function for r tending to infinity must become 0. Then for such integrands, there's no contribution from the semicircular arc, right? So this condition has to be satisfied, and those are okay for, it's 1 plus z square, 1 plus z cube, or whatever it is, it'll satisfy. Because this denominator will be higher, right, in power, so it can help you to make that go to 0. All right, so let's now understand this. This is the same argument, so I'm not repeating it, but I will. You have to put z per r exponential I theta and then check it, okay? And then same argument for r tending to infinity, the denominator is this can be approximated as r squared exponential of 2 I theta. So, so we have r here, 1 over r in the denominator, r tending to infinity. Because r is in the denominator, that pull this integral to go to 0. Okay, so the same argument. Yeah. So, so what we have is exponential, this is equal to, that is 0. Did I have an I there or I is there? Pi over e. Okay, so this tells me that minus infinity to plus infinity of cosine of x over 1 plus x squared dx plus minus infinity plus di sine of x over 1 plus x squared dx is nothing but pi over e. So the right hand side has a real part and no imaginary part. So compare the real part to the real part, imaginary part to the imaginary part of the function. So what you get is minus infinity to plus infinity cosine of x over 1 plus x squared dx is nothing pi over e. And then we also get, we are not asked to prove that, but you get automatically on the integrand we have solved. This is equal to 0. Alright, so we got that. So the original integral that I had to calculate was 1 over half of that. So that is nothing but pi over 2. So this integral, which is from 0 to infinity, is nothing but pi over 2. So we'll do more problems so you get, understand the how to use it. So important thing is to know how to calculate the residue. That's it, in a simple way. I mean, otherwise you're in trouble. And the right-hand side is 2 pi I times the residue of the function. If there are more residues, more pole enclosed in the upper half plane, you have to calculate all of them. That's also important. And the type of the contour that we want to choose will be dictated by the limits of the integration mostly. I mean, that's the one. And if you have even function from 0 to infinity, try to make it minus infinity to plus infinity because that helps us, right? I mean, to solve. So we will, you know, what if the function f of x is not multi-valued here? This is all single-valued function, okay? So along the path, there may be, you know, on the real axis, it may be blowing up. Then we define what's called principal value integration. And if the function is multi-valued, what do we do? I mean, we have to modify the contour, the type of contour. Okay, so these are two simple examples, but we will try to talk next time about principal value integration, Fourier integrals that we always have because they will have minus infinity plus infinity. Jordan's lemma, we'll talk about that, multi-valued functions. Okay, so those are other complications for this slowly include in the integral. But these are sort of simple cases. It illustrates why we are doing the Cauchy-Riesdy theorem. So basically, eventually we are trying, although it is complex analysis, complex function, we are trying to calculate real integrals through the complex analysis. That's also we are trying to do. Infinite integrals they are trying to do. So most of the time it's 0 to 2 pi. And of course, this is the most important thing. I cannot blindly use, you have to always give me the reason why it went to 0. In this case, it went to 0 because of this condition, because it satisfies this is your integrand, right? I mean, because you have 1 over, if it's so r is very large, you know, you'll have 1 over r makes it go to 0. So you have to check this condition. You can also say r times maximum value of the function. You know, if it becomes 0 for r tending to infinity, then I can make sure it goes to 0 in the upper half plane. And sometimes, you know, why you're asking, you know, we may have to close it because depending on the function, lower half plane because it becomes 0 in the lower half plane rather than upper half plane. So that may also be the reason why you choose to close the contour in a different way because it, you know, based on the function. Okay, let's say it's exponential of minus x or something. Let us say in the integrand, then you know you can close it, you know, which way it will, or exponential plus x, let us say. It may be easier to close, you know, make it go to 0. Let's say exponential minus x divided by something x or something like that, okay? So you may choose the contour to close in a different way to force the integrand go to 0, okay? Because x will be in the other direction maybe. You know, things like that will be some kind of things that we have to play with, okay? I'll give you some examples, maybe, homework problems, maybe after the next class so that you have all the types, all the cases, so that, you know, yeah.